Thank you again. And I think we continue now with Krish Bharuth-Ram that will speak about Mössbauer Spectroscopy at ISOLDE. Thank you, 𝛽. Can we share screen with Krish?
Let me get to... Okay.
Okay, go ahead.
So let me go back to the beginning. As Alice said, okay, sorry, let's get to this. Moessbauer Spectroscopy at ISOLDE CERN.
Yes, we see your slide.
Is that okay?
Yep.
And the outline,
maybe
for those
show it a slideshow, please.
Oh, I did have it on there. Okay.
Perfect. Thank you.
Okay. Firstly, just a few comments on what is the Moessbauer effect, and then what are the measurables which rely heavily on the hyperfine interaction between the probe nucleus and its surroundings, and then some examples taken especially from the work that we've done using iron 57 and tin 119 Moessbauer. And I'll show the periodic table of Moessbauer active elements and then some concluding comments. If you look at recoil in nuclear physics, and if you take a free nucleus that emits a photon, and the photon carries away energy, but it also carries away momentum. And then this demands that the nucleus then recoils in the opposite direction with the recoil energy, ER. So the energy that the gamma ray takes away then is the transition energy less the recoil energy here, okay? And this recoil energy is given by just this simple equation. ER is equal to 1 upon 2m E gamma over C squared. When an absorption of gamma photon takes place, this photon similarly brings to the nucleus a momentum. And so this difference in energy between the emitting state and the absorbing state, now there's a difference of 2e gamma in the photon that's incident in here. So no resonant absorption takes place. Now, if the gamma source is embedded in a crystal, then the energy goes into lattice vibrations that is induced in the crystal. And in those cases, small number, but important number, of cases where the recoil energy is less than h bar omega, then no energy is transferred to the lattice vibrations. And the recoil momentum then is taken by the crystal as a whole. So the mass that is entering this equation here is the mass of the nucleus, is the mass of the lattice. And what this means then is that the recoil energy is reduced considerably. It's almost zero. In fact, is zero. And so in this case, where the emitting nucleus is embedded in a lattice. The gamma energy approaching an identical nucleus then is equal to this transition energy, and so resonance absorption can take place. So the Moessbauer effect, which Moessbauer called the M effect, is emission of a photon without loss of energy to recoil, hot with thermal broadening, and its resonant absorption then by a like nucleus. The recoil-free fraction, this is determined by the fraction of emission events that result in zero energy transfer to the lattice, the so-called zero phonon events. And for a Debye solid, it's given by the equation. So what we see from that is that the recoil fraction is large and the gamma ray energy is small, because then the recoil energy is small. When the Debye temperature is large, and when the temperature at which you're doing the measurement is low. Okay. So required parameters for a Moessbauer nuclide then is that its lifetime should be about 10 to the minus 10 to 10 to the minus 11 second. Gamma ray energy from 5 to about 100, 180 keV. And the nucleus should then have reasonable magnetic dipole moment and reasonable values of electric quadrupole moment for the hyperfine interactions to take place. What are then the measurables? And the measurables depend on the hyperfine interaction. The first then is the E0 electric monopole interaction. And this gives us what is called the isomer shift. It just depends on the charge density around the nucleus in an absorber compared to the charge density around the nucleus in a reference material, and multiplied by the mean square radius of the nucleus in the charge state minus the mean square radius in the ground state. This gives us information on the charge state as well as on the lattice side of the nucleus in a lattice. The second interaction is the quadrupole interaction, and we should go from bottom up. And this interaction is just the interaction between the quadrupole moment of the nucleus and the electric field gradient at the site where the nucleus is located. So it works in the case of non-zero electric field gradient. If the field gradient is symmetric, spherically or tetrahedrally symmetric, then this effect is zero. But also it is important to see then is that the energy associated with the electric quadrupole interaction is proportional to m squared, the magnetic quantum number. And so you get the plus half and minus half substates, and the plus half and the minus 3/2 substates being degenerate. In the case of the magnetic interaction, it's just mu dot B, and the energy associated with this is m times g times the Bohr magneton times the field, the z component of the field. And your selection rules then are delta m equals 0 or plus or minus 1, and it restricts transitions to the 6 shown here. So what we observe is that due to the hyperfine interactions, where the probe nucleus is located, the energies are slightly now shifted from what they were in a free or an emitting nucleus. And we have to somehow compensate for this change in energy. And of course, we use the Doppler effect. and put the source on a drive unit and just drive the source back and forth. So it scans these energies here. And these absorptions then take place, where the energy that you're driving the source through or adding to the energy of the photon occur in resonance. Similarly, in this case, you're driving, the energy must cover, your drive energy must cover this as well as that change in energy. Okay? And so what you observe in an absorption spectrum, when it's just the electric monopole interaction present, a single absorption line, if it's shifted from your reference by a small amount, then it means that the charge density around the nucleus in your absorber has this small difference in the charge density around your reference material. And here again, this absorption takes place when that resonance takes place, and that peak comes in when the energy equals this. We call this the quadruple shift in energy, and the shift of the 0 point from your reference 0 gives you the isomer shift. In the magnetic case, this is what you get. And an interesting exercise, in the case of an iron foil, this absorption appears at minus 5.3 millimeters per second, a drive velocity. That appears as plus 5.3 millimeters per second. And an exercise that I set my students when I used to teach was, in energy terms, convert this scale from millimeters to electron volts. And of course, that's quite easy to do. It's 1.5 times the mass. If in the case of iron 57, it'll be half times the mass of iron 57 times the velocity squared. And of course, if you put in the numbers, you have a half 57 times 1.66 times 10 to the minus 27 kilograms times 10 to the minus 3 squared meters per second. And you get a number, 47 times 10 to the minus 33 joule. When you convert this to energy units, this works out to, well, 3 times 10, about 30 times 10 to the minus 13 electron volts. So what this displays, and although the effect, the number of xenon zero phonon events is small, this technique is extremely sensitive to very, very small changes in energy. How is this drive achieved? In a transmission mode, you have a sample and a detector here, proportional counter or a pin diode. The source is mounted on the drive, which is then supplied with either a sinusoidal wave or a sawtooth waveform to give you a linear change in velocity. Now, Moessbauer, the drive unit, if you read the history of Moessbauer's discovery, his drive system was a unit, 1 meter by 2 meters long. And of course, he used the old similar type of system that drives tractors today, but except on a more sophisticated scale. And he could get velocities of centimeters per second. It was Cantelite, who was a contemporary of Moessbauer's at the time, that developed the coupled loudspeaker system that we use today. So this is the approach used in transmission Moessbauer spectroscopy. And then most of the Moessbauer transitions are low energy transitions. So what you get in ideal cases, you more conversion electrons emitted than photons. So these become, conversion electron Moessbauer spectroscopy has become a very useful tool because the sample then is mounted in the detector and it contains the probes. If you're using an iron 57 probe, then it contains iron 57 in it. And these produces then, and the photons absorbed here produce conversion electrons, which are then detected in that. I'm sorry, I'm gone already to the next slide. At CERN, the experimental arrangement is slightly different. The beam comes in. If you're doing manganese, oops, I seem to have missed a slide. I'll get back to that. We approach, if you're doing iron 57, then instead of coming from cobalt 57, which is available as a source, we approach it from a radioactive manganese 57 beam, energy around, well, 40 to 60 keV, fluence 10 to the 12 per square centimeter, incident on a sample, which is held at 30 degrees to the beam. The photons from here are then incident on the detector, which is on a conventional drive unit. This detector is a parallel plate avalanche counter, which consists of 2 electrodes, one of them enriched in iron 57, and then electrons produced from this. The enriched electrode is then detected in the second. The photo here shows our students, Hilary Masenda and Wendy Slamini, during one of the experiments doing the setup. And the next slide shows the beam coming down along that axis. The ion chamber is here. The detector has to be lightweight, so it's made of perspex in which the electrons are then housed and mounted on the conventional velocity drive unit. And we use acetone gas as the detector gas. So emission Moessbauer spectroscopy, manganese 57 decays to iron 57, which then, with a mean lifetime of 140 nanoseconds, then decays to stable iron 57 and emitting also a 14.4 keV gamma ray. This lifetime is important because what it means is that any heat treatment that we apply to our substrate has a reasonable chance of addressing issues like annealing, radiation damage, etc. So the fluences, the implantation process induces a large amount of defects. It's of the order of 10 to the 3 per implanted ion. And this method allows us to study the interaction of the implanted MN Fe probes with the defects that they produce. Fluences typically are of the order of 10 to the 12 per square centimeter, and this is sufficient to record a Moessbauer spectrum. Okay. The concentration at the end of this time, a typical measuring time is of the order of 10 to the 16 per cubic centimeter, which amounts to 10 to the minus 4 atomic percent. And this makes possible the study of lattice location of the implanted probe, its charge state and annealing characteristics, diffusion, defect complexes, phase transformations at the atomic scale, and magnetic transformation, cluster formation, as well as paramagnetic relaxation. Here in this slide, I show an in-beam Moessbauer system which was developed by Counterlight, first at the GSI and then at the Hahn-Meitner Institute. And here at the Hahn-Meitner Institute, this system used to use 110 MeV argon, which Coulomb excites the iron 57 nucleus in an iron 57 foil, and this is implanted on 2 targets on either side while the main beam goes through. A requirement of this then is that you need samples 2 by 2 centimeters minimum diameter. And the photons from here are then picked up in the parallel plate avalanche counters. As example, I show you here a spectrum collected on a diamond sample. 2 by 2 centimeter diamond, natural diamond samples, not really available. So we used a synthetic diamond sample produced in the high temperature, high pressure process. And what this method did was to give us a good signature on the interstitially implanted ion. The problem with the high temperature, high pressure method is that it produces diamond type 1A, which has nitrogen located on substitutional site, single nitrogen. I had given a talk on this, on Coulomb excited recoil implanted Moessbauer effect in diamond at a meeting in Cape Town. And of course, Heather did crime in diamond, and the police were there in the audience wanting to know what I was talking about. Today, Moessbauer in 1958, well, in fact, he found the effect before 1958, but published a paper. The paper was published in 1958 on iridium-129, and he was awarded the Nobel Prize for this in 1961. In the US, Stan Hanna and his group showed the Moessbauer effect for iron 57. And to my knowledge, this was in fact the first in-beam experiment, because they used a DP reaction on an iron 56 target to produce iron 57 and implant it. The position today is shown here. All the Moessbauer nuclides shown in pink. There are today 93 Moessbauer transitions in 44 nuclides, but more than 90% of the measurements are done using iron 57. Well, I think I've shown this already. So in the case of iron 57, the critical state is the 14.4 keV state. This can be reached in 3 different ways, either through a cobalt-57 source, which has a half-life of 240 days. So most laboratories then that do in-house experiments use cobalt-57 as their source. And then at CERN, we approach it via the implantation of the radioactive manganese 57, which beta decays to the 137 keV level, and this decays then through the Moessbauer level. And then the third way is the Coulomb excitation that Counterlight developed at GSI. A typical Moessbauer experiment, if you're looking at a crystalline sample, you have to implant iron 57 into the sample. And in order not to cause too much lattice damage, the concentration have to be kept quite low. So a typical measurement to get a decent spectrum would take you 5 to 10 days. In-beam Moessbauer, as done by the GSI and HMI. Here, you need about 24 hours to get a decent spectrum, but the problem is with the effective time of any heat treatment that you apply. Here, the effective time would be equal to the decay time of the state. And so you have only about 100 nanoseconds for which any annealing measure that you adopt would be effective. In the case of manganese implantation, fluence of 10 to the 12 to 10 to the 13, recoil energy 40 keV, and that sometimes allows one to study the nucleus implanted in a damaged site, but then being recoiled into a good lattice site. Measurement time is about 10 minutes, and the effective time of any heating treatment is about 100 seconds. And here in this box, then, some information on the iron 57 nucleus. Okay. And what is important here is this constant alpha, which is the conversion electron emission probability. So 8 out of every 9 transitions from the 14.4 keV to the ground state proceeds by conversion electron emission. The line width of the 14.4 keV is 4.7 times 10 to the minus 9 eV. So the energy resolution is a factor of 3 times 10 to the 12. Here I show an example of a measurement on CVD diamond using conversion electron Mössbauer spectroscopy as implanted state, showing very presence of highly damaged structures, and a single line corresponding to iron at a substitutional site in diamond only comes after annealing at around 1400 K. Compare that with the emission Moessbauer system. Already on implantation, a small signal from iron at a substitutional site, and which increases then to about 32% of the total resonance area, already at 850 K. So it's extremely sensitive, produces less lattice damage, and gives information in a very short time. So what this means is that in a time of about 1 hour, you can do a temperature series of measurement on each sample. Better show all of them at one time. Yeah, our next project was actually driven by this paper by 𝛽-decay, which showed from theoretical calculations that gallium nitride and zinc oxide implanted or containing about 5% manganese should show ferromagnetism at room temperature. And I think Carl had a slide showing how the attempt to then look for room temperature ferromagnetism in a whole range of substrates following implantation of 5% transition metal just bloomed. Transition metal ion just bloomed after the publication of this paper. So what in effect is done is that you have a semiconducting material and you put in there an ion that also is magnetic. Okay. And this has enormous applications, for example, in a computer, because you can then combine the processing as well as the memory in the same chip. Okay. And we tried this on zinc oxide. And this is the spectrum that we got. And we are very happy that we saw magnetic structures at room temperature. And then we did a temperature series of measurements. And what you notice, as shown by the dotted line that I put in the spectrum, is that the peaks don't change with temperature, the peak positions. Now this means, had this been ferromagnetic order, then there would be a temperature dependence following the Brillouin curve. But our sextet shows no temperature dependence. We then follow this up with a magnetic field, angle-dependent measurements in a magnetic field. The picture shows the sample and the magnet was mounted just behind the sample, so the field was always normal to the sample. And this was measurements taken at 60 degrees in a field of 0.6 Tesla. And this was a measurement taken at 0 degrees. And if you look at the two spectra, you'll notice small but significant differences. This peak here, shown in the upper curve, upper spectra, is, sorry, this small one here is absent, very much weaker here. This shoulder is very much weaker here. And the relative intensities of these two are slightly different, but measurably so. And we're able to analyze this in terms of Kramer's doublets, which lead to spectra which displays superposition of sextets due to the plus and minus, M equals half state, due to the plus and minus, M equals 3 half state, and the plus and minus 5 half states. And this, of course, would be for the ion being now in a 5 half state. Okay. And so what we see then is a paramagnetic effect, and this paper was published, Applied Physics Letters, in 2010. One of the co-authors, well, there are 4 of us from South Africa there, one of them being Wendy Slamini, who was the first Black South African woman student to come to CERN. We followed this then with measurements with zinc oxide pre-implanted with carbon. The energy selected so that the implantation profile matched that of the ion in the diamond. And we had concentrations of 4 atomic percent, 1 atomic percent, and 0.4. And also had a zinc oxide sample implanted with argon 40 at 45 keV, and its fluence 1.5 atomic percent. Okay. The spectra in carbon implanted zinc oxide. A couple of motivations here was one, to check what was the source of the magnetism that we are, paramagnetism that we observed in zinc oxide. And secondly, there are several papers reporting the observation of ferromagnetic behavior of carbon implanted zinc oxide. And of course, what we see in the 4%, 1% implanted samples is just the doublet structure due firstly to defects induced by the implantation process, and a small contribution from the substitutionally implanted ion, obviously still with some vacancies in its neighborhood, because the signature comes as not as a single line, but as a doublet. With the sample implanted with 0.04% carbon, we see at room temperature structures in the wings of the spectra which disappear at high temperature. In the next slide, I show this on an expanded scale, and you then see quite, to us, evident magnetic component in the structure together with the magnetic distribution. And as we increase the temperature from room temperature to the higher temperature, the line width of this component increases. And from the line width, we are able to determine the relaxation time. And what we get, shown on this slide, this blue shows the zinc oxide, carbon implanted at 0.4. And here we have the relaxation rate plotted against T squared, where T is the temperature. And we see that the carbon implanted zinc oxide follows very well a T squared dependence. A similar result we had observed in aluminium oxide. But the undoped zinc oxide follows a T relaxation rate proportional to T to the power 9. And those on zinc oxide implanted with different concentrations of iron, 5 atomic percent and 8 atomic percent, also appears to follow a T to the 9 dependent, although in this case we don't have enough experimental points. In the expression for the relaxation rate, there are two terms that appear. If it's a Raman 2-phonon process, the first term is proportional to T to the 9. The second term is dependent on the Debye temperature. If in the high Debye temperature over T regime, the second term approaches the value 1. In the low Debye temperature to T ratio, the second term approaches T to the 9. So here, this then gives us can explain the T squared dependence we see here, and also explain the T to the 9 dependence you see here. But it also says that in this case, the probe is located at a high Debye temperature region. And here it is located in a surrounding where its Debye temperature is low. We could then imply a damage site for this and a substitutional site in this case. In the case of argon, implanted ZNO, quite strong structure, much stronger than in the carbon implanted zinc oxide case. After annealing, the structure is still there. And here we show the temperature dependent. See, at 600 K, it is still quite strong. So clearly the relaxation rate is much, much slower than in the case of carbon implanted zinc oxide. Again, here we have just 3 experimental points. We've also done some tin Mössbauer spectroscopy. Here, the tin isotope was populated by first implanting radioactive indium ion into our sample. And the Moessbauer transition in tin is this transition down here. The energy is 23.8 keV. The half-life of the state is 18 nanoseconds. So almost at the short limit of lifetime. And the line width then is comparatively very large. A recent development to our setup was a development that allowed annealing studies coupled with low temperature EMS measurement. And here what we show is a new addition to the sample holder. This has a drive that allows one to extract the sample, immediately shut off the area so the sample is on vacuum, and then it could be taken and immersed into a liquid nitrogen bath to allow Moessbauer temperatures, Moessbauer measurement at liquid nitrogen temperature. Some examples of that I'll show in a short while. Here, the first measurement that we did using indium implanted indium tin, should have been an N tin, in silicon oxide was the first measurement we did. And here we see the spectra. We can just about identify this first series is at low temperature from 119K to 240K. And then here we go from 300 to 630K. Okay. And you can see gradually the damage component disappears when you get to 630K, and the indium ion is occupying good substitutional site. Silicon carbide, again, this is 3C silicon carbide, so it's cubic structure, and so it is almost identical to that, except that every other layer in the silicon lattice has a carbon atom. And
Case, do you have time
1
is
minute
running here?
Okay. And so, but then in diamond, we get significantly different structure. The experiment I wanted to show as my last one was the indium tin implanted zinc oxide. These are the measurements on the left shown at the high temperatures going from 300 to 640K. And then on the right-hand side, immediately these measurements were done. The sample was put into liquid nitrogen, and these are the measurements. It had allowed us to see the disappearance of the tin in the 2+ state, but then reappear over there, much stronger and a different Debye temperature, so we could identify that as tin then being on regular zinc site, whereas previously it was in damaged site. And then finally, with your permission, that's our team, but what I want to show, Mössbauer spectroscopy in Mars, and if you compare the Moessbauer system here, this includes the drive, the source, the drive, as well as the preamplifiers and the electronics for summing this signal before it was transmitted back to Earth. It was carried in this Mars rover, and it was located down here. And 2 spectra. The second one shows the presence of hematite in red and goethite in blue. And these 2 are only formed in the presence of water. Hematite is rust that appears on iron that is left out in the wet. And of course, this was taken as the first evidence of the presence of water sometime in Mars history. And finally, Siyabonga. Thank you very much.
Thank you very much. Nice talk. Are there any questions? I can see no one in the chat. So